Alright guys, hypothesis testing. Most of statistics is about testing a hypothesis. Or testing a guess, if you like. It's like, I see this data set, I think it has strong correlation. Okay, I'm going to do a test to see if I'm right. It does have strong correlation. I'll do a Spearman or a Pearson test. I think this data set has a mean 20. Okay, I'm going to check it by doing some calculations and seeing if my hypothesis is correct. In hypothesis testing, we first have to state what our hypothesis is. What is our guess? What do we think is true? That's the null hypothesis. That's what we think is true, what we assume to be true. And then we do tests to see if it is true. If the null hypothesis is not true, the alternative hypothesis is true. If the alternative hypothesis is true, the null hypothesis is not true. This can take the form of, for example, the null hypothesis could be the mean of this data is 20. The alternative hypothesis could be the mean of this data is not 20. Okay. For one-tailed and two-tailed tests, the alternative hypothesis is different. If our null hypothesis is mean 20, a two-tailed test would say the alternative hypothesis states the mean is not 20. For a one-tailed test, the alternative hypothesis could be the mean is above 20, or it could be the mean is below 20. And we'll talk more about how this is significant later on. So the first example that I want to talk about is a binomial test. And I want you guys to imagine that we're doing coin flips and we're seeing how many heads we get. And we assume that our coin is fair. So we assume the probability of a success is 0.5. Now, for you, at which point would you start to question your null hypothesis? If you flip 7 heads out of 10, 8 heads out of 10, 9, at which point would you start to question your null hypothesis? Well, let's say we did a test and we flipped our coin 10 times. We assume the probability is a half that we get a head, but we get 8 heads. So we get 8 successes from 10 trials. Assuming the null hypothesis is correct, so you're saying probability of success is 0.5, the chances of flipping a coin 8 times is below 5%. It is below 5%. Now, most companies, most creators of a product, or in most statistical tests, the significance level, and I'll explain that, is 5%. Now, what it means, the significance level, is if you do a test, which, assuming the null hypothesis is true, occurs less than 5% of the time, but it did occur when you did your test, then you reject your null hypothesis. You say something's wrong. Some assumption I made must be wrong because I'm doing this test and it should only happen less than 5% of the time. Well, the only assumption I made was the null hypothesis, so we reject the null hypothesis. A binomial distribution can be represented as this, right? This is a binomial tree, and at some points, some of the tests cross the 5% significance level. There are less than 5% chance that we flip 8 heads. There's also less than 5% chance we flip 2 heads, and 1, and 9, and 10, and 0. Okay, so this is the threshold. This is the significance level. If we do a test that's over the significance level, we reject our null hypothesis. Now we're going to introduce a little bit more definitions that we need to learn. We have significance level, we have null hypothesis, and alternative hypothesis. Now we have critical region. So anything that is less than 5%, if the significance level is 5%, anything less than the significance level falls into the critical region. If we do a test that test would be 1% chance of happening, assuming the null hypothesis is true. That's in the critical region, so we reject our null hypothesis. Everything to the small side, everything lower than 5%, everything lower than the significance level is in the critical region. Scary. Okay, so null hypothesis, alternative hypothesis, significance level, critical region. I got one more definition for you. It's p-value. Every statistic has a p-value. Every test that you do produces a statistic which has a p-value. Okay? And the p-value means the probability that that test happens, assuming the null hypothesis is true, or any more extreme value. This means when we're doing calculations, we'll be finding this or this not equal to. So we'll be calculating cumulative probability distributions. Okay, let's go through some examples. This is data pulled from a question, and it's the null hypothesis says the probability of success is 0.7. The alternative hypothesis is that it's bigger than that. And we did a test. We did 10 trials, got 9 successes. Our significance level is 10%. The question is, does this test disprove the null hypothesis? So we need to find, did this test happen with a less percent chance than our significance level? So we need to use this and we'll calculate, assuming this is true. And we want the probability that x is at least 9. For this, we'll use our calculators, and we do scratchpad, statistics, distributions, binomial CDF, number of trials. So we'll get this. Number of trials is 10. Probability of success is 0.7. Is 0.7. Because we assume our null hypothesis is true until it has been disproven. Our lower bound is 9, our upper bound is 10, because that's the highest possible number of successes from 10 trials. And we get our answer is 0.149. Okay, so we have an answer, but what do we actually do with that? Well, we first realized that this is 15%, almost 14.9%. This is not below our significance level, so we do not have any reason or any evidence to reject our null hypothesis. Again, this number is not lower than this number, so we do not reject our null hypothesis. So that we might get could be one such as this, asking us to find the critical region. Asking us to find the critical region. So let me explain this question to you. This question is, a horse trainer says his horse knocks down fences 10% of the time. Less than 10% of the time. At most 10% of the time. A statistician looks at his horse and says, I don't think that's right. I think your horse is going to knock down more fences than that on average. So I'm going to do one test and see if my one test disproves your null hypothesis. Okay, so the horse runs around the field and he jumps over 9 fences. And the question then is, how many fences does he have to hit for this to be disproven? Well, intuitively, it's probably like 3 or 4. Okay, so for this type of question, we can guess and find the values. So we want to calculate the probability that the horse knocks down at least 2 fences. If that's wrong, we can calculate 3. And if that's not below 5% significance level, if that is not happening with a less than 5% chance, then we can calculate x is bigger than 4. And remember, it's a 0.1%. It's a 0.1 probability chance that he knocks down each fence. So knocking down 4 would be pretty significant. Let me get these answers. So the chances that it knocks down at least 3 fences is just over 5%. The chances that it knocks down at least 4 fences is very small. It's less than 1%. So the chances that it knocks down 4 fences is the boundary of the critical region. Why? Because it's a discrete probability, right? Binomial is a discrete probability. There is no 3.5 or 3.6 or 3.1, although we can see that probably around 3.1 is where it would cross, but this is a discrete probability distribution. So it's the next number after it crosses is the start of the critical region. So the critical region is x is greater than or equal to 4. Okay, now we're going to look at an example with the Poisson distribution. The good thing about this is we follow the exact same strategy. This is all the same. We state our null and alternative hypothesis. We do a test, assuming the null hypothesis is true. We see if that test was above or below the significance level, and we reject or don't reject the null hypothesis based on that. The only slight difference is in our calculation, but we're using a calculator for that anyway. So let me first explain a little bit about Poisson. What is it? This is review, but it's worth reviewing. So a Poisson distribution only gives you one value, and it'll look like this. So x is distributed with the Poisson distribution with average lambda. The only value it gives you is the average. The average what? The average number of events within an interval, usually a time interval. The best example that I usually give is how many buses come in a 10-minute period or a 20-minute period. The time interval is not given, the length is not given, that's not relevant. The average is relevant. So if in this 10 minutes 5 buses come, this 10 minutes 7 buses come, this 10 minutes 10 buses come, that's averaged, and that's what you got. For our test, we observe those 10-minute periods. We see how many buses come. From that, we either reject or don't reject the null hypothesis. Exactly the same as we've done before. In this example, 7.2 buses on average come per 10 minutes. For 20 minutes, that seems maybe half an hour. That seems like a lot of buses. Doesn't matter the time interval again. We see 5 buses. We don't see 7.2 buses, we see 5 of them. And the question is that test significant enough to reject that the average could be this? Intuitively, no, right? Intuitively, no. I see 5 buses in this time interval does not mean the average could not be 7.2. But we test. And again, we're testing for below or equal to. So we want to find this on our calculator. And we do the same process. Well, no. We do a similar process. We do scratchpad, menu, statistics, distributions, and we scroll down to Poisson CDF. And we put in our data. Lower bound is 0 because there cannot be less than 0 buses that come within a 10-minute interval, right? It doesn't go to negative. Okay, and we get our answer is 0.27, which is 27%. There's a 20% chance, 27% chance this could happen, or something more extreme could happen. This is the p-value. And since the p-value is not lower than the significance level, therefore it's not in the critical region, therefore we do not reject our null hypothesis.